Hi everyone, and welcome to this webinar about AVTECH's new cruise optimization service. A recording of this webinar will be made available as a link on the webinar page. If you have questions along the way, please type them into the question box and we will answer them at the end. Please note that you will only see your own questions. The agenda for today's webinar is a short introduction to AVTECH. We'll look at modern weather forecasting, what's available. We take a look at the background and the operational limitations that makes an optimizer service needed. We look at the optimizer and how it solves the problem. We'll then dive into some airline case study results where we have some fuel and time saving results for 737 flights. And finally, we have a Q&A section where we'll try to answer your questions. So to present myself, my name is David Ritter, CTO of AVTECH, responsible for developing and deploying our services. My background is in aeronautical engineering, and I'm also flying on an occasional basis as a pilot in the Swedish National Guard. AVTECH as a company is based in Stockholm. We're a public company listed on the stock exchange. For over 30 years, we've been pathfinders in aviation and really focusing on making flights and the ATM system more efficient. Our current services and product portfolio is mainly based on flight efficiency and improving safety and comfort of flights. And our approach and products are really customer focused. So we're really focusing on tailoring our services for our airline customers. Our vision is to provide the right information to the right user at the right time. Looking at the basics of everything, or the platform that we're basing all our services of, we have our 4D trajectory-based platform, which is really about communicating with the aircraft, retrieving the necessary parameters to build a four-dimensional flight trajectory. With this flight trajectory, we're able to combine with high resolution weather, really accurate weather, and provide safety improving and efficiency improving services. Some of the data that we retrieve from the aircraft is the active route, cost index, altitude, weight, ETA, and performance data. And all of this goes into live building a trajectory. So based on this trajectory, we're able to provide a number of services, making flight safer and more efficient. The Aventus Nowcast service is based on generating an optimized weather uplink to the flight computer, which really makes the flight computer calculation more efficient, providing better decision support and ETAs for the flight crew. Sigma service, where we take the four-dimensional trajectory and provide turbulence warnings and severe weather warnings along the flight trajectory. And we have the ProFlight EFB app supporting professional pilots with a complete weather briefing and in-flight optimization package available on the ground or in the cockpit. Current users of our services are major airlines operating a number of aircraft types, both short and long haul. And today's webinar will focus on our new in-flight cruise optimizer service. So this in-flight cruise optimization project was jointly initiated with the 737 operator Norwegian and also supported by the Swedish Energy Agency. Our initial idea was to work around the limitations of the Boeing 737, which has one of the most advanced flight computers, but completely lacks support for cruise wind data in more than one flight level. And by delivering this feature in a ground-based service, pilots can still get the decision support to optimize their flight. And in fact, the service we built is now able to calculate and recommend a truly cost-optimal flight profile, taking full detail of the atmospheric forecast into account. And this means that the service also outperforms the built-in flight level recommendation logic in other aircraft types, which now makes this service interesting for non-737 operators. Before we get into the optimizer service, let's have a look at the importance of an accurate weather forecast. I think it's fair to say that any cruise optimization service can only be as good as the quality of the weather data input. And at AVTECH, we made it our mission to use the best weather data available. And together with Met Office UK, we have created a unique aviation weather forecast, which we call 10K aviation weather. So let's start by looking at the proof of the quality. What you see in front of you is on a monthly basis, major global weather providers are benchmarked against each other. And the following graph shows the Met Office scoring versus the other providers, showing a consistently higher scoring result over time. We see the blue line in the graph is really Met Office result, which is placed as a 0, and all the other weather provider scorings are in relation to Met Office, and we can see that consistently better performance, better forecasting performance is achieved. Met Office is a global aviation weather provider, and along with NOAA in the US, they provide a standard aviation weather forecast, which is a global grid with 140K horizontal resolution. This is the data which is used by flight planning providers and the aviation service community. Internally, however, Met Office are running their forecast models at a much higher resolution, a 10-kilometer resolution. But much of the accuracy is thrown away when exporting and delivering the standard weather forecast. Met Office and AVTECH has therefore developed quite unique and much improved forecasts, which is retrieving the weather in real time from Met Office servers for the 4D flight trajectory. So we no longer have to export the high amount of data that would be generated by 10K into the AVTECH servers. Instead, we work with the data sitting in Met Office, which is really necessary at this resolution and detail of forecast. The result, as shown in AVTECH's wind uplink service measurements, is up to a 50% reduction of the wind forecast error. And this is really coming from a 200 times higher horizontal resolution. So we have 10K instead of 140K. We have a 2 times higher vertical resolution with 120 levels instead of the standard 70. And we're also doing a full-time interpolation, which means that we retrieve the weather for the exact time when the aircraft is passing a waypoint. This can be visualized. So looking at this in a visual way, we have in front of us the 140K forecast grid and a flight from London to Edinburgh, which you can see is covered by only 3 weather points in total, which may be okay when the weather is not changing. If we instead overlay 10K forecast, we can see that we now have many more forecast points to reflect the details and the changes in the weather throughout the flight. And on days when the weather is changing more rapidly, such as frontal passages, this is of course even more important. In next slide, we see the same behavior with turbulence. So we have the clearer turbulence forecast, 140K, which is barely usable as decision support. And now moving to 10K resolution, we can see that this is now starting to be really usable for making decisions. And this is in a horizontal, so looking at the turbulence horizontally. In our Sigma and ProFlight products, we have a high resolution. We're using this high resolution forecast also for vertical decision support, so how to avoid turbulence in the best possible way by giving the pilot a decision to descend or climb. So the demonstrated result when used in AVTECH's wind uplink solutions is, as mentioned, a 50% reduction of wind error in the flight computer, moving to a 10K forecast. And the graphs that we see to our right is from an analysis that we made with Lufthansa Cargo. It's based on thousands of flights and a quite global selection of routes. And we can see we can clearly see the reduction in wind error, but we also see a reduced variation in the wind error between days and flights. The end result is clearly a more accurate and more consistent forecast every day and for every flight. Now let's take a look at a few of the reasons why a flight is typically not operated in a cost-optimal way. So at the time when the flight plan is typically created and filed, which is probably 6 to 24 hours before the flight, at this time, the flight planning system aims to select optimal flight levels based on a standard weather forecast, so 140K, based on an estimated aircraft weight, based on estimated departure time. However, filing altitude restrictions, so restrictions because of traffic and ATC, will in many cases push the planned altitudes down and to a non-optimal profile. Moving to the flight execution stage, so in the aircraft before or after the takeoff, even an optimal planned profile may no longer be optimal. Aircraft weight may have changed to be different than planned. Departure time may be moved due to delays, and the weather has changed. In-flight route changes such as directs and reroutes will also make the planned profile inefficient and non-cost optimal. Now, what do we mean when we say a cost-optimal flight profile? The cost index is inserted into the flight computer before the flight and is a tool for the airline to ensure that the flight is operated in a cost-optimal way. Cost index is very simply just a ratio between time and fuel costs that affect the flight, and will, depending on its setting, provide a prioritization between fuel or time efficiency. Entering cost index 0 will result in a FMC speed selection for a minimum fuel consumption, so lower speed. Entering cost index 100 or whatever scale is used in the specific FMC and vendor system will result in an FMC speed selection for minimum time, which is higher. And the flight computer will, in this way, aim to cost optimize the flight according to the airline priority between fuel and time. This approach would work well if the flight was flown in an atmosphere with no winds or very uniform winds. If the flight, however, is operated in the real atmosphere, winds and temperatures in different altitudes will affect the ground speed. And this means that together with aircraft weight and cost index, the vertical flight profile selection for the flight will affect the total cost of the flight, and for each cost index setting there will be a cost optimal profile. Due to limited weather input in the flight computer will not be able to provide an optimum profile recommendation. So let's take a look at AVTECH's Cruise Optimizer service and how an airline can get the decision support to operate each flight in the most cost optimal way. So we know that the planned levels may not be optimal. We also know that a more optimal level can often be available from ATC if requested. And we've seen that FMC is not capable of calculating the optimal profile. And this is due to whether the FMC is really the tool that you have in the cockpit to provide the pilots with a notion what is the most optimal altitude. And it aims to do that, but weather data is typically only available at waypoints in the FMC. So it will not know the weather in between waypoints, and sometimes the distances in between waypoints are quite large. Weather data is only available for a limited set of altitudes. The FMC will allow 4 altitudes. So for each waypoint, it would know the wind in 4 different altitudes. This is a very limited set, and in the case of the Boeing 737, it's even more limited with only 1 altitude. So it only knows the wind at the cruise level. This, together with a simplified performance model in the FMC, really means that the flight computer will not be able to calculate an optimal cruise profile. And not flying according to the set cost index will mean a cost penalty. AVTECH's focus has always been on providing the best possible weather input to the flight computer, given its limitations. However, no flight computer will be able to take the full weather detail that we have available now into account. So the AVTECH solution for this is to, in real time, communicate with the flight computer over data link, retrieving aircraft weight, active route, cruise level, cost index, combining this with an accurate aircraft performance model from manufacturer performance data, and dividing the flight into small steps with using the great 10K weather forecast we have from ATOFIS, and to, on the ground, in a ground-based system, calculate the true cost optimal cruise profile based on up-to-date and highly accurate winds and temperatures for all levels. This is then delivered to pilots on the printer display, EFB, to support an informed decision of the flight level in cockpit. This results in flying really an optimal profile for the set cost index, really utilizing the beneficial winds and saving fuel or time depending on the airline priority, depending on the cost index. Problem at hand, to actually find the minimum cost flight path is to look at all the options, find the vertical route that is truly cost optimal. We solved the problem using a dynamic programming algorithm, and this is to guarantee a finding of the global optimum minimum cost, taking fuel and time into account. So we really divide the problem into small pieces. We have states and we have stages, where states represent the altitudes, stages represent the flight distance steps through the atmosphere. By utilizing an accurate aircraft performance model, the cost of each available step can be calculated, and for in each step there are decisions to be made, whether to remain on the level, whether to climb to a higher level, or whether to descend to a lower level. And combining all these steps, looking at all the combinations, this algorithm is really finding a true global optimum, which minimizes the costs. And we here talk about the equivalent fuel cost, which is the cost of fuel and time combined through the cost index. We see each stage is typically a 10-kilometer step. Each state is a flight level. The starting point for the calculation is the top of climb point. The end point is the top of descent point. So with this product, we're only looking at the cruise phase of the flight. The optimizer can be set to adhere to even or odd level restrictions based on the flight segments. So this is ATC restrictions. We can set limitations to the maximum altitude. So to apply maximum altitude restriction based on the airline-specific operational procedures. The model can also configure and the minimum time between steps can be fine-tuned. So to not allow the model to change level too often, even if it's more optimal. It may not be great for the pilots or ATC. We're doing the optimization in 2 steps. The first step is an initial calculation. Second step is a final calculation. We see the graph to the right here. We have the OFP profile is the purple line. We have an initial calculated profile, this green or turquoise line. And then we have the final optimum profile as the blue line. So really what we do in the initial step is to run an optimization calculation with low resolution weather and with larger steps, so typically 200 kilometer steps, to find the corridor where we roughly see that the optimized flight profile will be in. Based on that result, we can then go to our 10K weather solution and the Met Office and retrieve for the trajectory a high resolution corridor. And the final calculation is then run on with this corridor and much finer steps, 10 kilometer steps, to find the really optimal solution, optimal flight profile. We're also looking in the next step to add speed selection optimization. So that would be as a third step in optimization. Looking at the total process then, the optimizer is a ground-based service. It's easy to deploy because of that. We connect the service via ACARS and speak to the aircraft via ACARS. So first step is aircraft communication. So what happens when an optimizer calculation is triggered is that we talk to the aircraft, retrieve the data to build the 4-dimensional trajectory. We retrieve the standard weather forecast, 140K. We run optimization step 1, which is calculating, giving us a rough corridor. We then go and retrieve the 10K weather. And in the second optimization step, we do a final profile calculation using the high resolution weather. We then calculate the cost savings, so the equivalent cost savings between flying the optimal profile versus flying the planned profile. And finally, we format and deliver the results via ACARS or IP, internet, to the flight crew or the ground. Looking at the report that we provide, we have an easy to read format for the pilot. It's a very configurable format, and the report can be uplinked to either the display or the printer in cockpit, or an EFB device via an internet connection. This report provides the pilots with optimum step points, as well as the savings potential, the fuel and time. So we see the saving in terms of fuel, in terms of time, and in terms of the combination of fuel and time as equivalent fuel. And there's also identifying information, so for the crew to identify that this calculation was made for our flight and made for the set cost index and gross weight. Format is the report is available once the flight computer has been initiated. It can be set up as a manual request or as an automatic push. It could also be made available earlier if needed, based on flight planning data. So once in the air, an optimal cruise profile can be requested anytime. So whenever the flight plan changes, whenever there are changes, directs, or maybe the flight is delayed, really a new optimal cruise profile can be retrieved, can be requested by the crew, or triggered in an automatic way. What happens is that data is downlinked from the flight computer, and the optimized profile response is uplinked to the cockpit, either as a printer or as a display or as an EFB report. Now let's review a few operational results from running the cruise optimizer in a Boeing 737 airline operation, and where we then automatically get a comparison between the optimal profile and the planned profile. Looking at the first case, so what we see in front of us is the report on the left, and a visualization of this report to our right. And there we can also see what was the original planned trajectory. So in this case, we have a 1500 nautical mile flight. And we see this is a typical case where the planned profile steps can be fine-tuned. We see the black line is the planned profile, the green line is the optimal profile, and we see that the optimal profile is slightly different, similar but slightly different in the exact points where the steps should be made. And this you can see this gives us a fuel saving of 35 kilos, time saving of 74 seconds, and combined in an equivalent fuel saving, this is 49.4 kilos or 0.4%. Next case, we have a longer flight, around 1800 nautical miles. We see cost savings are available by initially climbing higher than planned, and mid-flight we see that there are favorable winds below that makes a step descent optimal. Fuel saving roughly 46-47 kilos or 0.5% of the cruise fuel. Next flight is a bit shorter, around 1200 nautical miles. We can see that the filed altitude is initially set very low, probably because of constraints. We can see that the optimal, but maybe not necessarily constrained, we can see that the optimal profile immediately goes higher and then makes a step at fairly the same point as the planning does. In total, we have 33 kilo fuel saving if the optimal profile can be achieved, which is 0.5% of cruise fuel, or more than a minute of flight time. Next flight is a nice one. We see it's a fairly long 2,400 nautical miles flight. We can see that the two profiles have a very similar shape, but that the filed profile is including roughly a 500 nautical mile step down. But the optimal profile, we see that with a similar shape, but it's moved. So we should initially go for a higher altitude. Probably the weather forecast at the time when the aircraft is reaching these favorable winds below, the segment of the flight where there are maybe favorable winds below, the weather has shifted, so really the optimum step down is later and not as distinct as the planned step down. We see a fuel saving of roughly 64 kilos, but interestingly enough, in this case, there's also not a time saving, but there's a time penalty, and this is really due to the optimization for the cost index. So the cost index is set fairly low in this flight, and we optimize for the equivalent fuel, where we see that we have quite a positive equivalent fuel saving if flying this profile. Next flight is a really short flight, filed at a very low level, flight level 190. And basically we see the optimal profile is of course flying, going higher. And if achieving this, there's a quite big, as a percentage-wise, quite big saving, 119 kilos, 90 seconds. Next example, We have a fairly long flight, 1600 nautical miles, and dramatic fuel saving. In this case, the planned flight level is certainly not optimal. Initially, we should go for a higher. The flight should go for a higher altitude, and a total of just below 400 kilos of fuel, 380 seconds of time could be saved by flying a more optimal profile. Next flight, a bit of the same, really. 1400 nautical miles, roughly. Also quite large fuel saving, roughly 3% saving potential. 436 seconds of time by following an optimal profile instead of the plan. Next flight, similar, also large fuel saving, 270 kilos, 221 seconds. Next case, 1200 nautical mile flight, again, large fuel, large time saving if the optimal profile can be performed. Here we have a little bit shorter, a bit over 1,000 nautical miles domestic flight. We see that the flight level is really filed in a non-efficient level. Flying at a more efficient level really gives, in this case, a potential fuel saving of 1%, 64.5 kilos, and 232 seconds of time. And finally, we see that cost savings are available by, in this case, fine-tuning the step points. While we have a small initial part of the flight where it's capped at the low altitude. Of course, a higher altitude setting at that point is more beneficial. We see fairly similar step points as the flight planning for the step climbs. But approximately mid-flight, we see that stepping down to a lower altitude for the other half of the flight would be beneficial. In total, 0.4% of cruise fuel, 38 seconds can be gained by following an optimal profile. So, as a summary of these results, this project and this study is ongoing. We can see an optimal profile based on the 10K aviation weather from Met Office. Really provides a different profile than the OFP, and that most flights can benefit from an optimized profile, optimized cruise levels. We see in this case study results showing fuel saving potentials in a range from 0.5 to 6.5% of cruise fuel. And we also see that the calculated saving can provide a quite valuable measurement of the efficiency of the flight profile. So what are the potential gains by being able to fly in an optimal way rather than the filed flight plan? We see typically two different optimization scenarios or combinations thereof, where we have a fine-tuning of an already planned step climb point, or we have quite different or completely different optimal altitudes that were not planned due to more up-to-date data and due to not suffering from the filing level restrictions. We see that this product always provides the cost optimal profile for the current active route, and it supports a dynamic cost index. So if dynamic cost index is used within the airline, this is a product that truly supports it and provides pilot decision support in order to fly that profile when it can be achieved. And it's available today as an easy to deploy and inexpensive service. It can be delivered to pilots and dispatchers before and during the flight. And even though I would say all the potential fuel saving may not be achieved or cannot be achieved because of ATC restrictions and of other operational reasons, if even a fraction of the potential could be achieved for the individual flight, this will still add up to quite a significant fuel saving on a yearly basis for the airline. We see the example here is at the 1% fuel saving. For a typical flight en route, we have a 75 kilo fuel saving, which adds up. If you think this sounds interesting, don't hesitate to contact us for more information. And we also invite airlines to try the service for free and verify the savings on their own, in their own operation. So contact us at sales@avtech.aero. Thank you for listening. And now starts the Q&A section. So please type your question in the question box and we'll do our best to answer. Okay, so we have a question from Volker at Eurocontrol. Whether we're taking into account standard ANSP profile restrictions and early descents, handover requirements into the flight optimizer. And basically the answer, the flight optimizer is really it's really an improvement to the FMC logic that aims to provide guidance for the pilots to optimize the flights. And whatever the pilots enter into the FMC as waypoints and airways procedures, we will calculate based on the 10K resolution weather and cost optimal profile. So this is really to replace the recommendation of FMC altitude. It's not going to take into account ATC restrictions. I hope that makes sense. So it's really a replacement of the FMC logic providing pilots with decision support. And then the pilots will have to request from ATC based on a really informed decision, a more optimal cruise altitude. We have a question whether the ACARS uplink requires FMC AOC data link functionality. Yes, is the answer. It does. Some of the requirements, so I think what are the requirements might be a good question for running the service. What is needed from the airline? And this product can be run in different ways, but running it live, so live and connected to the flight, it would require an ACARS data link functionality. So the AOC data link needs to be enabled. As an airline, you need to have ACARS, of course. We would then work with the airline in terms of building. So for the specific aircraft type, AVTECH would build a performance model of the aircraft. This is based on the high resolution performance tables, so manufacturer engineering performance tables, which are available in the airline. So AVTECH would use that to build a performance. model. Then everything happens in AVTECH's ground system. So we communicate with the aircraft. The setup is very similar to what we have with our Aventus and Sigma products, where AVTECH integrates. We can do that in a really easy way. We can integrate using our ACARS ground address, and just via ACARS data link, speak to the aircraft, run our optimizer, and deliver the results to the cockpit. We can also integrate more. It depends on the airline needs and requirements. We have several airlines where we integrate more closely with their ACARS management system. So ACARS messages would go from the aircraft down to the airline's ACARS manager, and then be forwarded to AVTECH. AVTECH would respond with an optimizer result back to the airline and the airline uplinks. So we're fairly flexible in the way we can do it, but to make it easy to deploy for airlines, we can do most of the process in AVTECH. So it's really at minimum involvement of airline IT, I would say. So we wanted to make this service really easy to deploy. We want the thresholds to get this type of information into the cockpit to be really low, so you don't need any new equipment. It takes use of the equipment which is there already. Next question is on high-risk weather coverage. Does it include all continents? And the answer is yes. The high-resolution aviation weather, so the 10K weather from Met Office, is global. So we have the same resolution, the same quality weather products all over the globe, which means that this solution is completely unhindered geographically. So it can provide decision support, optimal decision support for any flight, any part of the world. Next question from Volker is whether the fuel savings is for the whole flight. The fuel saving that we show in the examples and that we will provide to the pilot is for the cruise segment of the flight. So we only determine a fuel saving in between basically the top of climb and top of descent, that we define as the cruise segment. This is a comparison, so we do a calculation and compare the operational flight plan levels versus the optimizer levels. So this is really the potential saving if you could fly this optimal profile. But it's on the cruise segment of the flight. Robert asks, beside more accurate weather, what is the difference between our profile optimizer and let me see. I don't see the rest of the question, but probably other solutions like Pace and Honeywell. I would say the main difference. Accurate weather, like you point out, is a main difference. No one else has access to this type of weather forecasts. And we measure this a lot, and it's actually performing really, really well. The ease of deployment is the second part. We've really focused on, just like with our other products, Aventus and Sigma, to make this solution easy to deploy in the airline. So that I would say no new equipment is needed. So provided that you have an ACARS connection to your aircraft, provided you have the AOC data link functionality turned on, which means that the CMU, the communication unit, and the flight computer can actually speak. Then we're good to go. We have a solution for you, so you don't need anything more. And I think that's probably the biggest difference from other solutions. Really easy entry level. It's not an investment. We provide this as a service. You don't pay anything upfront. It's pay as you go. You can test it quite easily. The only work required is on AVTECH side, really, with a little bit support from the performance department in the airline for AVTECH to set up the performance model for the aircraft. Next question from Carlos. Where does the ACARS uplink generate from? So I think this refers to where. So AVTECH, as mentioned, we have our own ground address in the ACARS network. So we can either directly uplink from our address to the airplane. We have some airlines that pick this solution. We can also connect directly to the airline and provide the uplink in any type of format via the internet or ACARS, and then the airline can provide it as part of its EFB package, integrated in its EFB solutions, or uplink it themselves to a printer or display in the cockpit. Next question from Salman from Ethiopian. Whether let's see, can we provide a certificate? Okay, yeah. So I would say, Salman, please contact us, and we'll talk about next steps to try this out. Next question from Shamsi. Whether the webinar is available on the website afterwards. The question is yes. It will be posted sometime after this webinar closes. So you can re-listen if you miss something. Then we have a question whether this service can be added into our ProFlight service. The answer is yes. This is something that we're working on right now, and that we'll roll out really soon. So we're going to be able to, ProFlight users will be able to get this product and get an in-flight optimization directly in the ProFlight app, together with the weather, high resolution turbulence and weather support, and the new IATA turbulence feed that we're adding right now. We have a question from Gulat, whether we can use anti-ice and turbulence actually experienced by the aircraft to influence and override the optimizer. So the answer is yes. We can use turbulence, and AVTECH are partnering with IATA on experienced turbulence. So on their feed, and we have a really good high resolution clear air turbulence feed from Met Office, which is a forecast, but really good. So we can use that to influence the optimizer and prevent recommendations into turbulence. That can certainly be done, and probably will be done. Robert asks, how much do you charge for the service? So I think we this is fairly early days commercially for the service. So I think the service will be fairly inexpensive. I don't want to give a price for it here and now, but please contact us at sales@avtech.era, and we'll talk about this. We are giving this as a free trial for an airline interested in this. You will be able to try this as a free trial for a limited period of time. So please get in touch with us. Then we have a question whether the service works only for the 737 aircraft, and I would say the service is maybe more needed in the 737 aircraft, where the FMC functionality is really not optimal when it comes to altitude recommendations, because it only takes the weather into account for one altitude. For other aircraft types, the service still provides much more optimization than what the FMC can do, and it's based on the same basic logic that the weather data into the FMC is really limited. It aims to give an optimal altitude recommendation, but it's only for here and now, I would say, in the aircraft. It looks at the current winds and temperatures, and it blends that forward with the forecast that it has. Our product will provide a much more accurate result, and to give a total, give the flight crew in any aircraft type the total optimal profile as a decision support. And with that, I think we are wrapping up. So if there are no other questions, we'll be wrapping this up. Thanks a lot for listening, and don't hesitate to get in touch with us. We're eager to work with you. Thanks.